So remember last time where we left off was how to use that constants page to figure out what's called the standard cell potential for our battery. So we look up our oxidation reaction that happens at the anode, our reduction reaction that happens at the cathode. We take the value at the cathode, subtract the value at the anode, and we get our potential for that battery in volts. Okay? And we said that if that standard cell potential is greater than 0, then this is a battery that will spontaneously react, that will get our flow from our anode to cathode. And if the standard cell potential is less than 0, then that would be a non-spontaneous battery. Okay, but remember, kind of a bit of a misnomer. Non-spontaneous doesn't mean that it doesn't happen at all. It just happens in the reverse direction. So really what that means is that you switched your anode and your cathode, right? Your battery is going to run in the opposite direction of what you thought. Okay, and again, we said that these words, spontaneous, non-spontaneous, they remind us a lot of delta G, all right? And indeed, there is a relationship between our standard cell potential and the delta G of these reactions that are powering our battery. Okay, so what is that relationship? So remember, our standard cell potential is in units of volts. All right, and a volt is a joule per coulomb. Joule is, of course, the unit that we use for what? Energy, absolutely. And coulomb's kind of the new one. Does anybody remember what coulombs are units for? Charge, right? So this is energy per unit of charge. That's what a volt is. Delta G is, of course, an energy, though. Okay, so what we could say is that if we knew the charge, we could multiply that by our standard cell potential. Okay? Because of convention, it's actually the negative Q that we would want. All right, and that would give us units of joules, okay? So this would be it's called the maximum amount of work that battery can perform. It's moving a charge over a certain distance, performing work. All right? So for a given reaction, what's the net amount of charge that's being transferred? We're going to use what's called Faraday's constant. Faraday's constant has this value of 96,485, and the units are coulombs per mole of electrons. Okay, so again, coulombs are this unit of charge. We can talk about the charge of an electron in units of coulombs. It turns out that if you had a mole of electrons, 6.0221 times 10 to the 23 electrons, the charge in coulombs would be this Faraday's constant, this 96,485. All right, so our formula, we're going to stick this all together. Negative n, where n is the number of moles of electrons in our equation. F is Faraday's constant. And then that E naught cell is again our standard cell potential. All of these together would tell us the amount of work that our battery could perform the amount of energy that can be devoted to doing work, what we've called before free energy. So we have our relationship between our free energy and our standard cell potential. All right, so let's just go back to our previous example here. Now if we use our new equation here, we're going to plug in our value for our E that we calculated, our standard cell potential is that 1.10 volts. We got Faraday's constant, that constant value, 96,485. Okay, I'm going to write volts in joules coulomb so we can see our units. Okay. And if I have my balanced chemical equation for this oxidation reduction reaction, how many moles of electrons are being transferred per mole reaction? 2, right? So that's what I'm going to use for my value for N. Got to stick that negative sign on there. All right, we get this gigantic number, negative 212,267. What are my units on that number? Let's look closely. We said 2 moles of electrons times Faraday's constant, which is coulombs per mole of electrons. So moles of electrons cancel out. I messed this up, sorry. Faraday's constant is coulombs per mole electron, not joules per mole electron. Which is important because now what's going to happen to those coulombs? They're going to cancel out. So I'm left with units of joules. All right, remember for our free energy, we usually report in kilojoules. So if I'm going to transfer this to units that we're more familiar with, it's negative 212 kilojoules. Which is spontaneous or non-spontaneous? Spontaneous, right? It's a negative delta G, and it better be, right? Because we said that a positive E cell was going to be spontaneous as well. So these say the same thing. And this is an absolutely massive value for delta G. Okay, and that is true of most battery chemistry. You will get this large, hundreds of kilojoules values for delta G. These are reactions that very strongly favor the products if you've set up your battery correctly. Okay, so anyways, big number like this. This is what we're going to expect when we talk about our batteries here. All right, going back, we can even go a step further, because we have this relationship that we've utilized before that relates our equilibrium constant of our reaction to the delta G of our reaction, right? So one of those equations on our constants page from last exam was that our equilibrium constant is equal to E to the negative delta G over RT. Oh, delta G not, sorry. All right, so given this relationship here, I want you to combine this equation and this equation to give me my equilibrium constant in terms of that standard cell potential. All right, so all I'm going to do is substitute in negative NFE for that delta G in my equation. Those negative signs will cancel out, so I'll be left with NF E naught cell over RT gives me my equilibrium constant K. All right, and so let's just summarize here. We said that if E naught cell was greater than 0, that means our reaction is spontaneous. That means that the delta G naught is what? Greater than or less than 0? Less than 0. Also means it's spontaneous. So then what about my value for K for this reaction? Should it be a big number or a little number? Greater than 1 or less than 1? Better be greater than 1 if we have a spontaneous reaction, one that spontaneously proceeds towards our products. We would expect K to be a number greater than 1. All of these point to a spontaneous reaction. So let's just convince ourselves that that is the case. We're going to plug in our values here. E, I'll make it really way too big. For this particular reaction, it was 2 moles of electrons times that Faraday's constant. Times our 1.10. If we look up that value for our ideal gas constant R, that's that 8.314 joules per Kelvin. And what temperature should we be using here? Yeah, how do we know it's standard? Because we got the naught going on, right? We're talking about delta G naught, E naught, where actually we haven't really talked much about it yet, and we're going to circle back. This is going to be important here. But we've always been talking about the standard cell potential, right? So that keyword standard means that we're talking about this battery under standard conditions. Which is that 25 degrees Celsius. All right, or converted to Kelvin, 298. All right, so I punched this all into my calculator. Notice that my units will all nicely cancel out. All right, I get 1.62 times 10 to the 37. Is that a big number or a little number? That's like an absurdly large number, 10 to the 37. This is a reaction that ridiculously favors the products, which is sort of what we would expect with such a large negative delta G value, right? In the hundreds of kilojoules. So all of these pointing to the same idea, this very favorable reaction will very favorably proceed towards the product side here. All right. Cool. So one last thing to kind of plug in here that we've discussed before. We're talking about our E naught cell or delta G naught. And remember, these little knots refer to standard conditions. Okay? And standard conditions were actually this very stringent set of conditions. One we just talked about, the temperature is necessarily 25 degrees Celsius. All right, but remember, standard conditions are even more stringent than that. They actually tell you how much of each reactant and product you have as well. The concentration of everything has to be 1 molar under standard conditions. And any gases that you have to have a pressure of 1 atm. Right? So a very specific set of initial conditions. That's what this potential is good for. That's what our delta G is good for, is just this standard set of conditions here. Right? So what if I want to run a battery at anything other than 1 molar solution? How am I going to figure out what the potential is? All right, so remember that we had this equation when we were talking about free energy. The free energy, the delta G, without the knot, right? So this is under any conditions. Is equal to that standard free energy value, delta G naught, plus RT natural log of what important variable? That lets us do anything outside of equilibrium? Q. Right? And remember, Q is the key here. Q is the key in this particular equation when we were talking about free energy. It's going to be the key here. This is your equilibrium expression. All right, but remember, the magical thing about Q is it's that same equilibrium expression, but when you plug in values outside of equilibrium. Equilibrium expression with values outside of equilibrium. Okay, so now let's go ahead and plug in our expression that we just built for this delta G naught. Right? Remember that delta G naught is equal to negative NF E naught of our cell. All right, and so if we have delta G, we're going to have an analogous sort of equation here. NFE cell without the knot. Right, and then we still have that natural log of Q, which allows us to enter any conditions outside of standard state. All right, so I want everybody just to practice your algebra. Take a second and solve for that cell potential. That's what we're trying to figure out here, our cell potential outside of standard state. All right, what am I going to do to both sides? divide by that negative NF. All right. On the left-hand side, that'll cancel it out altogether, leaving me with E cell. All right. And then because of how this addition works here, it'll cancel out from this one term, but not this one over here. So what I'm going to be left with is E naught cell minus RT over NF natural log of Q. All right, if you want to see this the long way real quick. This thing here, right, that addition is really messing you up. You can't cancel out that NF altogether. So this is going to be the same as negative NF E naught over negative NF plus RT natural log of Q over negative NF. So it cancels out from that one term, but not the other one. That's how I get my final answer here. I don't know what happened to that Q. All right, and so what is this equation doing for us? Similar to what we saw with delta G, this is going to allow us to determine our battery's potential at any conditions outside of standard state. All right, so for example, our battery that we were talking about was zinc plus copper ions gives us copper and zinc ions. So everybody take a second and build me that expression for Q for this reaction, for this battery. All right, remember, I'm going to do my equilibrium expression. So what over what? Products over reactants. And which one of these products do I not have to bother to include in my equilibrium expression? My solids, right? My copper. So this is just the concentration of zinc ions divided by my reactants, the concentration of copper ions. All right, so that would be my expression for Q. If these concentrations were 1 molar, then fantastic. I would just calculate the standard cell potential and be done, right? But if I wanted to make these concentrations anything else, I'm going to have to use this expression here in order to determine what the potential of that battery is. All right, so let's do one of these from scratch here, going all the way back to beginning. All right. I want to make a battery. Using aluminum and bromine. All right. That's what I want. I got aluminum on hand. I got a bunch of bromine on hand. I want to make a battery out of them. Okay? So I'm going to go to our constants page, and you're going to pick out the 2 half reactions that we would use in this battery. All right, so I got 1 for bromine. Okay, so for the sake of being able to see everything a little easier, I'm going to copy and paste this to another page. Come on. Okay. Whoop. So here's my 1 reaction. Okay. And then here I have my reaction with aluminum. Cool. Okay. So I want you to take a second and try to think which reaction is going to happen at the anode and which reaction will happen at the cathode. There we go. All right, so if I'm looking at this chart here, again, my 1 reaction, my bromine reaction was here on my chart. My aluminum reaction was here on my chart. Remember that this chart is organized. We're at the very top, the largest E0 value. These are, well, so first of all, actually, let's just take a look at this equation. What's written here, an oxidation or a reduction reaction? Right, remember, losing electrons is oxidation. So if it's an electron is the product of a reaction, it's an oxidation reaction. Here it's a reactant. So these are all reduction reactions. And the way that this table is organized is that the ones at the very top are the best reduction reactions. And the ones at the very bottom are the worst reduction reactions. All right? But the ones that are the worst reduction reactions are the best oxidation reactions, right? So that means I want my reduction reaction to come from the top of this list, and I want my oxidation reaction to come from the bottom of this list. All right, otherwise my battery is going to go in the other direction. All right, so my reduction reaction has to come from the top, so that's going to be my bromine. This will be my reduction reaction, which means that my aluminum is going to be my oxidation reaction. Which happens at the anode. Remember what we're supposed to remember here. From anode to cathode. So my reaction that releases the electron is going to occur at the anode. That's my oxidation reaction. And my reduction reaction is going to happen at the cathode, the one that accepts the electron. So my cathode half reaction is the liquid bromine. And look, these even are charge balanced for us if we grab it from our table. Okay, so my cathode half reaction is this reduction reaction. For my anode half reaction, my oxidation, what am I going to have to do to this equation I get from my table? If this is the reduction reaction, what am I going to have to do? I got to flip it. All right, I got to have my electrons on the product side for my oxidation reaction. So I'm just going to take what's on my table here and flip it. So now this is aluminum solid going to the aluminum ion and 3 electrons. All right, so these are my 2 reactions that are going to power my battery. My oxidation reaction at my anode, where aluminum metal is turned into an aluminum ion, and then my reduction reaction at my cathode, where my bromine is going to accept 2 electrons and become the bromide ion. All right, so everybody take a second and give me my overall reaction for this battery. You need to sum up these 2 half reactions. Okay, so again, I'm going to sum up these 2 reactions, but what am I going to have to make sure cancels out when I sum them up? The electrons, right? So I got to square away these electron values here. I'm going to have to take this first reaction and multiply it by 3, and take this second reaction and multiply it by 2, so I have the same number of electrons on both sides. So for my overall reaction, I get 3 Br2s plus 6 electrons and 2 aluminums. All right, and then 6 bromide ions, 2 aluminum ions, and again, 6 electrons. All right. This balancing step is really important because remember, in order to get that delta G, I have to know how many electrons are being transferred, how many moles of electrons, right? So these 6 electrons that I'm going to cancel out for my balanced chemical equation, that 6 will be very important when I go on to calculate my delta G. All right, that's how many moles of electrons are being transferred in this reaction. Okay, so before we can do that, let's calculate our standard cell potential for this battery, our E0 cell. All right, given these charts here, I want everybody to take a second and calculate that standard cell potential for this battery. All right, so what minus what? Cathode minus anode. Okay, and because of the way that this formula is given, you don't like flip the sign of anything. It's already done for you basically because it's a subtraction problem. So you just grab the value for the cathode and subtract the value for the anode off your table. You don't have to flip signs or anything like that. So 1.09 minus negative 1.66 gives me a standard cell potential of 2.75 volts. All right. So 2 things that we want to note about this E0 cell calculation that I think is kind of easy to mess up, right? Just grab the values from the table. Don't flip the signs. Okay? And the other thing is because a volt is a joule per coulomb, right? This value is given to you in terms of energy per unit charge. So notice that our balancing from our chemical equation didn't factor in anywhere where we were calculating that E0 cell, because that potential is really the energy per unit charge. Okay? These values from our balanced chemical equation will come into play when we're calculating delta G, but when you're calculating the E0, you don't pay, the balancing of your chemical equation didn't affect how you calculated that value. All right. So then we can take this, and now everybody take a second and tell me the delta G0 of this equation here, or of this reaction here, of our battery. First of all, do we expect it to be a negative number or positive number? Negative, right? Because we have that positive E0 cell, so we should get a negative number. All right, delta G is negative NF E naught of our cell. Again, what's the N? Moles of electrons. How many moles of electrons are being transferred in our overall reaction here? 6, right? So that's why we need our balanced chemical equation. That's all charge balanced. So we can see how many moles of electrons are being transferred. Times that 96485. I guess for being good about units. 6 moles of electrons. This is coulombs per mole electron. Times now that 2.75 joules per coulomb. All right, punch that into our calculator. We get negative 1,592,000 and some change there. This would be in joules, but again, we like to report our delta G in kilojoules. We still get this massive number. 1,592 kilojoules is that standard cell potential. All right, so then let's go a step further and get our equilibrium constant for this reaction. Try to get as much information about this reaction as we can here. Right, so for our equilibrium constant, we just take that expression that we had for our delta G naught and plug in our delta G equals negative NFE cell. All right, so plugging in those values, we get E to the 642.56, which is such an enormous number that it breaks my calculator. I honestly can't even go a step further than that because it's just some ridiculously huge error. My calculator gives me what's called an overflow error, which means that it's got too many frickin' digits to keep track of at that point. It loses track, right? Bottom line is we have an enormous number here because we have such a huge negative delta G value. So we'll just leave it as E to the power of 642.56. A very large number. Okay, I did not expect that, so hopefully this next step doesn't break the calculator as well. So that's all good if we want to figure out our potential under standard conditions. Okay, but now let's take our balanced chemical equation and try to figure out for conditions outside of that standard state, what would be the potential of this battery. Okay, so here is our balanced chemical equation. You need to build me that equilibrium expression Q. Oh no, we're fine. No, because when you plug in that, it's negative. It is plus RT natural log of Q in the normal equation, but when you're substituting in that delta G, it's negative NF that you end up dividing by. So if we go back to here, you're dividing by that negative NF, which is how we get a negative sign on that term. All right, so I'm going to do products over reactants, right? So I have my bromide ion. What am I going to do the concentration of bromide? To the power of 6. Concentration of my aluminum ions to the power of 2. And then what goes on the bottom? What is it? Nothing, right? Because I got a pure liquid and a pure solid here. So my equilibrium expression is just the concentration of my 2 ion products. Okay? And again, if those concentrations were 1 molar, then I would just look at my standard cell potential. But now let's say that the concentration of bromide is 1.5 molar. And the concentration of aluminum ions is 0.25 molar. Okay, everybody take a second and calculate the potential of this battery under these conditions. Oh, crap, never mind, we got no time. 2.75. Minus 8.314 times 298 over our 6 times Faraday's constant times the natural log of 1.5 to the 6th times 0.25 squared All right, and we would get 2.75145, blah, blah, blah. Okay, so really didn't change our potential very much at all. We'll see because it's the natural log of Q and because our value for E tends to be pretty large. There's not much movement there depending on conditions. Volts.